So just to remind everybody what we talked about last time I was here. We talked about Galileo in reference to the Galilean mentality of the Ross spiral. And what we concluded when talking about Galileo is even though we attach his name to this dynamical mentality, which remember is based on motion, it's based on change, that Galileo's own mentality was pretty firmly fixed in the previous mentality of the spiral, which was the geometric. That all of Galileo's proofs, all of his diagrams, all of the way that he thought about motion was in terms of line segments and triangles, and all of his proofs were geometrical proofs. They didn't use calculus, they didn't use what you would recognize if you're taking, for example, Dr. Parshall's advanced physics class right now. You wouldn't be able to look at Galileo's writings and recognize, oh, that's the physics I'm learning right now in school. You wouldn't even be able to look at Newton's writings and say, that's the physics that I'm learning right now in school. So this dynamical mentality of the sort of primary idea being motion and change was just born with Galileo, but it didn't reach its climax until at least 200 years later. What I want to talk about today is kind of the climax of that mentality, the Galilean dynamical mentality in the middle of the 1800s. And then what comes next, the birth of the next mentality. So I'm going to start today's lecture, which is a very similar lecture to the one I give in what's called the Dynamical Systems course, or just sometimes the Chaos course, that some of the faculty and some of the Innovation Lab students take, that Ralph Abraham developed for the Ross School. Because the beginning of that course is also about how we go from viewing the universe as determined by simple equations to viewing the universe as a much, much more complicated system, and how we deal with that in terms of how we think about doing science and what we're doing when we're doing science. So I'm going to start this lecture as I did the lecture from my other class in 1812. The reason for this is a couple of things. One, there's lots of interesting things going on in 1812 in a lot of different domains. I was actually asked when I taught college, this was like about, it was exactly 2 years ago in 2012, we had a sort of festival where people from English teachers to history teachers to math teachers to science teachers gave a little 200th anniversary of 1812 talk and talked about what was going on in their field in 1812. And what I chose to talk about was the Great Comet of 1811-1812. The Great Comet of 1811 and 1812 was one of the brightest comets ever seen. It was visible for 260 days, so almost an entire year in much of the northern hemisphere. It was as bright as Arcturus or Vega. Those are the second and third, or third and fourth brightest stars in the sky. Second and third brightest stars in the sky. So it would have been pretty much the brightest thing in the sky other than Venus and Jupiter. And it had a tail. Well, the coma, which is the head of the comet, was about the size of the full moon, and the tail was 25 degrees long. To get a sense of what that means astronomically, when you're talking about distances in the sky, you measure those distances in degrees. A good rule of thumb is that your fist, if you hold it at arm's length, is about 10 degrees in the sky. So you can imagine 25 degrees is 2 fists and a half. So picture something kind of that big in the sky the whole year long. And it was really spectacular, not just to astronomers, not just of interest to astronomers, but it found its way into the popular culture of the day, and it found its way into paintings and into literature. This is a little excerpt from War and Peace, which was written about 50 years later, but takes place in 1812, and the section talks about Pierre looking up at the sky, and almost at the zenith above Prechenetsky Boulevard, conveyed and surrounded on every side by stars, and distinguished by its white light and its long curling tails, to the tremendous brilliant comet of 1812. And so the comet of 1812 was something that people reading this in 1869, 1870 would know about and sort of remember as part of the cultural memory. Here's a painting from 1820, just about 8 years after the comet faded from visibility, by William Blake. It's a series of little panels, little tiny wood panels. And this little monster in the front is the main focus of the painting, but if you look behind him through the magic of Photoshop, there is something which looks very much like a comet, and most people suppose that that Blake's inspiration for this comet was the comet of 1811 and 1812. So when a big event like this happens in the sky, it leaks into the cultural memory. People use it as a point of reference. We're not immune to that today. It's before your time, but when I was in grad school, there was a major astronomical event, which was that a comet, you couldn't see it with the naked eye, but you could see it with a small telescope, actually ran into Jupiter. The name of the comet was Schumacher-Levy 9. And what happened was it was on a crash course with Jupiter. As it got closer and closer to Jupiter, Jupiter's gravity pulled it apart into pieces. And so this long string of pieces of comet hit Jupiter one after another over the span of about a day and a half. And as Jupiter spins, you can see black dots on the face of Jupiter. That's the place where the comet plunged through the atmosphere, and then Jupiter turns, and then the next piece plunges through, and the next. So you can see the black circles where it just kind of punches a hole in the clouds. And you can see this through a modest-sized telescope. When I was in grad school, I was in charge of the university's telescope as the grad student who was TAing the astronomy classes. So we took students up, and we could actually look at Jupiter through the telescope and see this. So it was an interesting thing that happened. It was the first time that astronomers ever got to watch something hit a gas giant planet like this. And it's interesting to ask what happens when a comet hits a planet doesn't have a solid surface like the Earth. It's just clouds all the way down. So it was a really interesting astronomical event. But a few years later, in 1998, there were, not coincidentally, 2 movies that came out that same year about the Earth being hit by a comet or an asteroid. The better of the two being Deep Impact, starring Morgan Freeman as our real first black president. And then the crappier of the two being Armageddon, starring Bruce Willis and Ben Affleck, the one that you're probably more likely to have seen, and probably one of the worst depictions of science in a movie ever that has ever been made. I could go a whole hour-long talk about all the things that are wrong with Armageddon, but because a lot of you guys haven't seen it, I won't do that. But it's something that you shouldn't get me started on. This phenomenon of comets being something that are make their way into pop culture and used as touchstones and as symbols and as references goes back thousands of years. Comets up at the top. This is something called the Bayeux Tapestry. It's from the 1070s. So it depicts events leading up to and during the Norman conquest of England in 1066. So this is a cloth tapestry. It's 200 feet long. So this is just a little piece of it. It goes and goes and goes and goes. And so it depicts history linearly along the tapestry. And these people right here are pointing up at that comet up there that's going across the sky. And the words above their heads, Isti Mirant Stella, mean they marvel, or they're marveling at the star, or they're wondering at the star. And so these people are saying, hey, look at that, what's that in the sky? You may know that comets for thousands of years were viewed not just as interesting things that happen in the sky, but they're viewed as omens or portents or harbingers of doom, or however you want to think of it. They were viewed as bad things to happen, and usually indicators that something was about to go down, that was not good. The reason for that is fairly simple. For thousands of years, the heavens have been the sort of source of what we think of as regularity in the universe. The moon goes around every 29 and a half days. The Earth spins around every 24 hours. The Earth goes around the sun every 360 some days. And it's always the same every year. We use it to make our calendars and decide when to plant our crops and figure out how old we are and remember how long ago something happened. All of our timekeeping, from days to months to years, is based on astronomical regularity. Okay? If we look at the planets, the same thing. Mars goes around every 2.5 years. Jupiter goes around every 12 years. Saturn goes around every 35 years. Everything in the heavens seems to have been predictable. And going all the way back to cultures that lived in BCE, 10,000 years ago, there were architectural monuments, things like Stonehenge, things like Neolithic temples in Europe, that were basically built as calendars to keep track of, oh, this is the time when Sirius rises at such and such a place on the horizon. That means it's going to get cold soon. That means it's time to harvest our crops or whatever. So the heavens are seen as a source of regularity going back thousands and thousands of years. It's the source of our mathematics. It's the source of our science in a lot of ways. When something happens in the sky, some bright thing shows up with a long tail that nobody's ever seen before, and it gets brighter and brighter and brighter every day, and then it goes away again. People are like, what the hell was that all about? The heavens are always the same. I go out at night, it's always the same constellations and the same Mercury, Venus, Mars, Jupiter, Saturn, the same 5 planets. You can't see the other ones without a telescope. So when something happened in the sky that was unexpected, it was seen as a threat to the order of the universe. This guy sitting here, almost right under the comet, King Harold, dies in the Battle of Hastings about 50 feet that way. Okay? So the comet is there as an omen, okay, as a symbol that, okay, shit's about to go down, right? The comet is a symbol of the bad tidings that are about to befall King Harold there. Most of us are a little more mature in our thinking about comets nowadays. We now know what a comet is. It's not just a mysterious fuzzy light in the sky. It is basically the word that was coined by astronomers back around the time Halley's Comet came by last, which was 86, 87. Is a sort of dirty snowball. And around this time of year, if you go out to the parking lot or along the edge of the road where the snow plows have plowed up all the snow, but they've also plowed out a lot of gravel and dirt, and you pick up a big handful of dirt and gravel and ice and pack it all together, that's basically what a comet is. It's dust and rock and ice all kind of packed together into a ball that can be anywhere from the size of a boulder to the size of this building, to the size of East Hampton, just depending on the size of a comet. There's comets of all different sizes. Most of the time, they just sit there looking like a blob of kind of black ice and aren't particularly interesting to look at. It's only when they get very, very close to the sun that we notice the comet is there. Because they're made of ice, and it's not just water, I mean some water ice, but also like ammonia ice and methane ice, things that have a lower boiling point. As they get closer to the sun, that ice starts to evaporate. So a comet, as it gets closer to the sun and goes around and around the sun, develops this tail. And the tail always points away from the sun because the pressure of the solar wind and the particles coming out from the sun blow the tail back. So when you look at the tail of a comet, it might always look like it's moving that way, but this comet is moving this way, and the sun is blowing its tail back. So comets orbit the sun in these highly irregular paths, highly elliptical paths that are very different from the planet's orbits, which is why we only see them for a few months at a time. We only see them when they're close to the sun, that ice evaporates, the tail forms and blows out, and then when it moves around the sun and goes away again, we don't see it again. Okay? This is what a comet looks like up close. This is one particular comet, Hartley 2. Is the name of the comet. Comets are named after their discoverers. So the person that discovered this was named Hartley. This was the second comet that he or she discovered. This was photographed by a spacecraft that was sent to sort of intercept the comet in 2010. The spacecraft was named Deep Impact, yes, after the crappy movie from 1998. So this is a photograph that shows what's sometimes called the nucleus of the comet, just that dirty snowball. But you can see that this comet is starting to warm up and evaporate, and these sort of geysers of steam, or, I mean, it's hard to think of it as steam in space, but these ices are turning into gas, and that gas is evaporating, and the tail will be forming shortly. So all of these places where there's sort of stuff blasting out of the surface is the ice evaporating and the comet developing a tail. Comets have orbits that range from entirely inside the Earth's orbit to going way out into the solar system. The 1812 comet that I started out talking about, if we ask, where is that 1812 comet now in 2014? This is a picture of the whole solar system, right? The sun is at the middle. You can see the orbits of Jupiter, Saturn, Uranus, Neptune, and Pluto. Pluto's the tilty, crazy one. That's why we don't call Pluto a planet anymore, because it has a tilty, crazy orbit, among other things. The other reason is that it's made more like a comet out of ice than it is like a planet out of rock. But that's what we think of as the solar system, right? Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, solar system. Right? But that's not the end of the solar system. There's all kinds of crap floating around out there further away than Pluto. If we ask, where is the 1812 comet now? Okay, right there. Okay, about at least 2 times, almost 2.5 times further away than Pluto. Notice that the orbit is highly elliptical. It's not round. It's this stretched out ellipse. And notice that it doesn't behave itself in orbit nicely in a plane the way the other planets do, right? All the planets go around the sun kind of in the same plane, and this comet is orbiting in this highly eccentric orbit. And the space outside of Pluto is full of these things. Some of them may be as big as Pluto. In fact, we know for a fact there are some out there that are as big as Pluto. Another reason why we don't consider Pluto a regular planet anymore is because there's, as far as we know, dozens, if not hundreds, of things out there that are as big as Pluto, these kind of big leftover ice balls that have been hanging around out there since the solar system formed. If we ask, when will this finish its orbit? So it's coming out this way. It's going to finish its orbit out here somewhere, come around, come back to the Earth. When will we see the 1812 comet again? We will see it again in 4907. So unless we have had our brains uploaded into a computer and achieved immortality, we probably won't see, none of us in this room will see the 1812 comet again. If we ask, when did it come back before 1812, it was 1285 BC. Okay? So this is a comet that takes a couple thousand years to make its way around the sun. Not all comets are like that. Some go around and never come back. Some go around in a couple of years. A typical comet goes around in 40, 50, 60 years. They go kind of out to where Jupiter and Saturn are and come back. Halley's Comet, for example, I saw in 1987. It has a period of 70-some years. I don't remember the number off the top of my head, 72, 74 years, 76 years maybe. I probably won't see it again. I mean, I don't know. I was 16 when I saw it the first time, so maybe if I, cut down on the fat and exercise more, if I live to be 98 or whatever, maybe I'll see Halley's Comet again. You guys will probably see Halley's Comet when you're, in your 50s or so. So what's all this about comets? Why am I talking about comets? The reason I'm talking about comets is because comets are one of the first examples of a recognition of the power of physics to determine regularities. Halley's Comet that I was just talking about, probably the most famous comet, not because it's the brightest comet. Sometimes it's bright, but it's usually kind of a meh comet when it comes around. Halley's Comet is the most famous comet because it was the first comet whose return was predicted by someone. In other words, it was the first time someone realized, hey, I bet that comet is the same as this comet and it's going to come back again at this particular time. That person was Halley, and he's credited with being the first person to discover that comets are not these irregular things that just happen in the sky. They are things that orbit around the sun just like the planets do. Okay? And that's going to be what we stress in a minute. If you ask yourself, how can we know that this comet is going to be back exactly in whatever that year was, 49-something-7? How do we know that the time before was exactly 1285 BC? The reason is we know the laws that govern the motion of objects, and we know the laws of gravity. And if we know the laws that govern the motion of objects, and we know the laws of gravity, we can predict what those objects will do. All of you have a program on your computer called Starry Night. You can open it up right now, type in today's date, and see where all the planets are in the sky. Jupiter is really nice, and you go out right after sunset, you can see Jupiter. It's the brightest thing in the sky. It's about kind of here to the left of Orion. I think it's kind of in Taurus. And you can go and ask that program, where would Jupiter be tomorrow night? Where will it be a week from now? Where will it be 6 months from now? Where will it be in the year 4987? Okay? How does your computer know where Jupiter will be in 4987? Because it knows that Jupiter follows predictable rules that are based on physics. Whose physics? Newton's physics. So we talked about Newton a little bit the last time I was here. Newton wrote his most important book, the Principia Mathematica, Mathematical Principles of Natural Philosophy, in 1687. And in the Principia, he set out his laws of motion. We talked about Newton's laws of motion a little bit last time. Everybody probably knows them, even if you don't remember them, right? Object in motion remains in motion in a straight line forever and ever unless something exerts a force on it. Force equals mass times acceleration is the second law, and so on. Well, what Newton's laws allow us to do is to make predictions about the motion of an object if we know something about three things. One is just where it is at some point in time. So say we're looking at the moon, okay? If I want to know where the moon is tomorrow, I need to know where the moon is today. So I need to assign a position to it. So three numbers. To define the position of an object in space requires three numbers, right? Because we live in a three-dimensional universe. If I want to know where is this ball, okay, I can say it's 1.5 meters from the floor, and it's 3 meters from that wall, and it's 6 meters from that wall. And that tells me exactly where that ball is in space. So x, y, and z are three numbers, okay? So I know where it is at one point in time. If I know what direction it's moving, I have another, it's really three numbers, but another number, which is its velocity, okay? Where is it and how is it moving? If there are no forces acting on the object, if I just know those two things, I can tell you where it will be at any point in the future, because Newton's first law says if it's moving with that velocity, it's going to keep moving with that velocity forever and ever and ever and ever and ever. So if I want to know where it is after a year, I just multiply 1 year times the velocity, and that tells me how far it's gone. Unfortunately, most things in the universe don't do that. Most things in the universe have forces acting on them all the time. If I throw this ball across the room, it doesn't move in a straight line forever and ever and ever. Okay, it moves in a curved path, and then it bounces all over the place because the wall exerted a force on it and the floor exerted a force on it. And so its motion is complicated. But I could still predict it if I knew the force. In this case, the force of gravity, or the force of the wall when it hits it. Okay, if I know the force, I can use Newton's second law, which says force is mass times acceleration. What is acceleration? It's a change in the speed. So Newton's second law tells you if you know the force on something, how much does its speed change? So for example, if there was a force pulling this ball down, its speed would change from that direction to that direction maybe. And now I know where it is and what direction it's moving, so I can tell where it'll be, say, a second from now, or a nanosecond from now, or a year from now. Now it's got a new position. I know where it is now. I know where it's going. If I know the force on it, that tells me how that velocity will change. If I know how it will change, I can predict where it will be in another second. Instead of following Newton's first law and going where it was going to go, it goes here instead. So Newton's laws allow us to calculate a trajectory for an object. In other words, a path through space and time. It's here now, now it's here, now it's here, now it's here, now it's here. And all we need to know is where it is at one point in time and the laws of motion that govern how it gets to the next point in time, and the next point in time, and the next point in time. Newton did this for simple motion, and he did it for gravity. In other words, he explained the mathematical law that tells how strong gravity is between two objects, which means all we need to know is the position of all the planets in the solar system at one point in time, and you can calculate where there will be in a year or 100 years or 1,000 years with basically perfect accuracy. So that's how the Starry Night program on your computer works. Okay? If the source of the force is gravity, we just need to know the law of the gravity. If the source of the force is electrical attraction, we just need to know the law of electrical attraction. That was discovered by a guy named Coulomb in the 1700s. If the force is magnetism, we just need to know the equations for magnetism. This sets up a situation where there's an approach to doing physics that is started by Newton and then matures over the next couple hundreds of years, which is this idea that if we know what's happening in the universe now, it's a fairly simple matter to predict what will be happening in the future. So we can predict how the moon goes around the Earth. We can predict how the Earth goes around the sun. We can predict how comets go around the sun. And no longer do we view comets as these things that appear out of nowhere, but comets are just as predictable as the planets. Why do I bring up comets and why do I bring up predictability in context with 1812? because something else very interesting happened in 1812, which is this guy, this French guy, Laplace, published a work called The Analytical Theory of Probability. And in 1814, a couple years later, he added a little appendix to it called a Philosophical Essay on Probability. And Laplace puts Newton's idea of how to do physics into a very succinct and maybe a little bit shocking form, the way he states it. Laplace says this, okay? Your French probably isn't that good. Well, maybe a couple of you can read this in French. I'll translate this for you from Laplace. He says, "We may regard the present state of the universe, where all of you are now, where the moon is, where Jupiter is, where the Andromeda galaxy is, as the effect of its past and the cause of its future." Okay? So wherever the universe is now is a result of the things that happened in the past to get it here, and whatever's going on in the universe now will be the cause of everything that happens in the future. An intellect, which at a certain moment could know all the forces that set nature in motion and the respective positions of all the items of which nature is composed. If this intellect were vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. Okay, what is Laplace saying? He's saying, imagine a really powerful intellect. You can imagine God, or you can imagine a computer the size of a galaxy, right? That knows where every atom in this room is, and where every planet in the solar system is. Now, just at one instant in time. And it also knows Newton's laws of motion and the laws of electrodynamics and the laws of thermodynamics and the laws of quantum mechanics. It knows all the laws that govern how objects interact with one another. All that machine needs to do is calculate what happens next, 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 and it can tell what will be happening in the future. Okay? A year from now, 100 years from now, 1,000 years from now. Okay? We can accept that mostly for comets and planets. But Laplace is saying that this is true down to the tiniest atom in the universe, including the atoms that you're made out of. Which means if I knew where all the atoms were in your body and in your brain, and where all the atoms were around you that were feeding you light and information about your surroundings, Laplace's intellect, and this intellect is sometimes referred to as Laplace's demon, okay? Laplace's demon would be able to record all those positions of the atoms in your brain, figure out from the laws of physics what they'll be doing in a minute, 5 minutes, an hour, and be able to predict all of your behavior for the rest of the day, for the rest of your life. Okay? It would know everything about the future, everything that happens in the universe. Okay? This is a philosophical outlook about the universe. It's called determinism, which says that, or suggests that, or believes that, however you want to think about philosophy, whatever is happening now in the universe causes what happens next, which causes what happens next, which causes what happens next. That's all that happens. Atoms exerting forces on one another, which means that what you will be doing when the bell rings and you leave this class at 11:15, okay, is 100% predictable if you're as smart as Laplace's demon or God or a supercomputer the size of a galaxy. Okay? So this is more than a method for figuring out where Jupiter is going to be next week. This is a philosophical outlook on the universe. It is saying that the universe is determined entirely by physical laws and nothing else. And the future is just as certain as the past. Okay? Laplace was friends with Napoleon. And there's a story, which may or may not be true, that he gave a copy of his book on celestial mechanics, how the planets move, okay, to Napoleon. And Napoleon said, where is God in all of this? And Laplace responded, I have no need of that hypothesis. Okay? In other words, Laplace didn't need God in celestial mechanics. All he needed were Newton's laws and the laws of physics to move things along from one point to another. This is not just a statement about science, right? This is a philosophical statement about the universe, that the only thing happening in the universe are mechanical, predictable, physical laws. Okay? Whether you believe it or not, it was a very powerful idea. Okay? Laplace is speaking specifically in his book about comets. And he says something about them which is important, which is that we can recall in the past, not so long ago, that if there was an unusual rain or an extreme drought, and if there was a comet that had just appeared with a long tail, or there's an aurora or an eclipse, all unusual phenomena in the sky were regarded as signs of celestial wrath, which is what I was saying before. So, for example, he gives an example of a comet of 1456 that spread terror through Europe, that was already thrown into consternation by the successes of the Turks, and who had just overthrown the Lower Empire. This star, meaning this comet of 1456, after 4 revolutions, in other words, after going around the sun 4 more times, okay, has excited among us a very different interest. The knowledge of the laws of the system of the world acquired in the interval, in other words, between 1456 and now, Laplace's now, have dissipated the fears begotten by ignorance of the true relationship of man to the universe. And Halley, having recognized that this comet was the same as those in 1531 and 1607 and 1682, announced that it would return again in 1758 or the beginning of 1759. The learned world awaited with impatience this return, which was to confirm one of the greatest discoveries that had been made in the sciences. Okay? Laplace says, Clairaut, I never really heard of this Clairaut guy, but he did something very interesting. He then submitted to analysis the perturbations which the comet had experienced by the action of the 2 great planets, Jupiter and Saturn. So in other words, this guy Clairaut looked at the path of Halley's comet and considered not just the gravity of the sun, but when it comes out here where Jupiter and Saturn are, Jupiter gives it a little pull, and then when it goes by Saturn, Saturn gives it a little pull, and that messes up its orbit a little bit. So he calculated that, and he fixed the exact perihelion, the exact time that it would come closest to the sun, as April 1759, and this was actually verified by observation. And this is the kicker. This is why Laplace is someone I talk about here. The regularity which astronomy shows us in the movements of the comets doubtless exists in all phenomena. So comets have gone in a couple hundred years from being symbols of the universe going crazy and being unpredictable to, in Laplace's time, symbols of the fact that everything in the universe can be predicted, that the regularity of comets exists in all the phenomena of nature, whether that's planets or the wind or living organisms or presumably inside your own head, that they're just atoms and molecules following predictable laws. This is a quote from around the same time that says about the same thing. I'll just skip to the end. This is a book on astronomy by Mrs. L.H. Tyler in 1837 talking about comets, and she ends it with saying, "At present, only the most uneducated regard comets as portending calamitous events." So we no longer think of comets as being unpredictable. In fact, we think exactly the opposite. So that's 1812. Okay? Laplace lays it out fairly clearly that this is the way we believe the universe works. And physics and astronomy proceed according to this assumption. Okay? I'm going to talk now about just an example from the history of astronomy about how powerful this idea is. In these 2 guys, Messier and William Herschel, lived around the same time. Their lives overlap significantly. Herschel, in 1781, was looking through his telescope, saw something that wasn't supposed to be there, wasn't on the star charts. What did he think? Probably a comet. Anytime you're looking at the sky and see something that's not supposed to be there, it's usually a comet. So he writes this little paper, an account of a comet on Tuesday, March 13th, between 10 and 11. I was looking at Gemini. I saw something that appeared not quite like a star, and I assumed it to be a comet. And then he talks about every day he looks at it to figure out exactly where it is in the sky, and he figures out its orbit. What he eventually figures out is that this is not a comet, this is a planet in a nice round orbit. It's a planet further away from the sun than Saturn, and it's a planet with the same sort of regular orbit that Jupiter and Saturn have, and we now call this planet Uranus. So that's 1781. Herschel discovers Uranus just by accident, which is the way most people discover things in the sky astronomically. You're just poking around with your telescope and you see something that's not supposed to be there. The discovery of Neptune in 1848 was very, very different in terms of how it happened. Okay? Neptune was discovered by Leverrier. And the way the discovery of Neptune happened is by observing Uranus, not by seeing Neptune by accident. And what was discovered was that if you calculate where Uranus is now, how fast it's moving, what the gravitational forces of the sun pulling on it, and predict where should it be next week, and then next week, and then next week, and then next week, what you find is that you're wrong. You look at Uranus next week, and next week, and next week, and it's not quite where you thought it would be. What does that mean? Well, it could have been taken to mean maybe Newton's laws of physics are wrong. Maybe we can't really predict where the planets are. Maybe Uranus has a mind of its own and it's just following its own laws of physics instead of Newton's first and second laws and the law of gravitation. That's not, obviously, what people concluded. What people concluded was maybe there is something else besides the sun pulling on Uranus, something else exerting a gravitational pull on it. Maybe there's another planet outside of Uranus's orbit that's given it a little bit of a tug away from the sun, and that's why Uranus is never quite where it's supposed to be. So what they did was figure out, in order to explain how much we were off, where does that other planet have to be pulling on Uranus? And they didn't just look around the whole sky trying to find an extra planet. They looked right there where they predicted that planet should be. And they discovered a planet right there. Okay? So Neptune was discovered, not by accident. Neptune was discovered using Newton's laws of physics and using a tiny discrepancy between what we observed and what we predicted to say, that's not quite right. There must be some other force pulling it, and that's where it must be pulling it towards, and that's where the planet must be, and bang, there it is. Okay? So the tables of Uranus's position were published by this guy named Bouvard, and the deviations from the projected orbit told Leverrier where to look, exactly where to look, and he found it there. Fun fact about Neptune, it was discovered in 1846. Just 3 years ago was its 1-year anniversary. In other words, from 1846 to 2011, Neptune has only gone around the sun once. Okay, so that gives you some idea of how slowly and how far away Neptune is, how long it takes it to orbit the sun. So what does this tell us? This tells us that this time period from, say, 1800 to 1840 is the pinnacle of this Newtonian idea that we can tell what the universe is doing by observing it now, deriving some rules, making a prediction. Observing it now, deriving rules, making a prediction. This deterministic, and the word that scientists sometimes use is paradigm, which is it's a big, complicated word, and I'm very careful not to use it lightly. But this idea, this framework for how you do science. What is science? Science is the act of observing the universe very carefully to figure out what's happening, figuring out some rules that tell how the universe gets from point A to point B, and then predicting what will happen next. Okay? This is the climax, then, of what we call the dynamical mentality, the Galilean dynamical mentality. From 1609, 1630, Galileo kind of coming up with the idea of measuring velocities of objects. 1687, Newton writing the Principia. To, not quite 200 years later, people are now using that paradigm to discover planets based on these predictions. Okay? So that's the mid-1800s. Let's go back to 1812, because there's something else interesting happening in 1812, which is people are just now starting to not just use physics to make predictions about the world, but use physics to sort of exploit the world and get it to work for them. One of the first things that happened in 1812, to go back to this year again, is there was the first commercial steamboat service anywhere in the world. By commercial, I mean you pay some money, you get on a steamboat, it takes you across the river or whatever. I think it was in Scotland. The name of that first commercial steamboat was the Comet. Okay? This is a painting of the Comet from 1816. Why the comet? Because, like I said, everything was about comets in 1812. We were still thinking about that. Oh, what should we call our steamboat? Oh, remember that comet from a few years ago? Let's call it the Comet. So this is the first commercial steamboat running in Scotland in 1812. Okay? Also, if you guys are learning about industrialization, industrial revolution, you know that a big part of that is figuring out how to get work out of machines. This is a picture of a very simple steam engine. John Robertson is the name of the guy with the cane in the foreground. But this is a machine that's built to turn a big wheel by heating up water. Okay? Almost all steam machines work the same way. Almost all of our electricity that we get today is still made by heating up water, turning into expanding steam. That expanding steam pushes a piston or turns a turbine and spins some big wheel that does work. Whether that's the wheel of a steamboat or a wheel in a factory or a wheel in a power plant that turns a magnet that makes electricity, it's the same principle, which is you're using heat to expand something to do work. Okay? Work is a very specific term in physics. We're adding heat to this water, we're turning it into a steam. What we get out is work. Work in physics is force times a distance. If I exert a force on something and move it from one place to another, I've done work. Okay? And that work could be moving a steamboat across the river, it could be turning a drill to drill a mine, it could be moving a train down the tracks. Whatever it is, your goal, if you're an engineer, let's say, in the beginning of the 19th century, is to figure out how to get as much work as possible from a certain amount of wood or a certain amount of coal or whatever it is you're burning as your source of heat. So people were concerned in the 1800s with the question of how do I get work out of heat in the most efficient way possible. So people began studying, well, what is heat all about? What is heat? Okay, how does it happen that when I rub two things together, they get hotter? Okay, what does it mean to even say the word heat? And so the science of studying heat and what it does and what it is and how it moves is called thermodynamics, literally the motion of heat. And thermodynamics really kind of starts here in the 1820s or so. The discovery that's made pretty early on is that heat itself is just motion. Heat is not a kind of stuff. Heat is the motion of stuff. And this is a discovery that had to be made. I mean, you guys have all been kind of told this since you were in elementary school and probably haven't thought of it very much. But in the 1600s, 1700s, people thought of heat as a stuff. Like heat is a thing. Okay, if I have my cup of tea, which is still kind of warm from bringing it in at the beginning of class, and I say the tea is hot, what does that mean? That means there's water in here, and there's tea leaves in here, and there's heat in here. And the heat is a third substance in the cup. It was sometimes called caloric, if you know the word calorie. Okay, it comes from the word for heat. So caloric was a kind of stuff that was in here in addition to the water. How did it get there? Well, when I put my tea kettle on the fire, somehow the fire transferred caloric from whatever was burning in the, I made this with an electric tea kettle, but let's imagine it's 1800, right? I throw some wood in the fireplace, I set it on fire, I put my tea kettle on it, the fire is releasing caloric from wood and putting the caloric into my tea. That idea hung around for a long time, and people had to really think hard about heat to get rid of the idea that heat could be a kind of stuff. One of the people that was really instrumental in this was a guy named Count Rumford, who worked in an armory for England. He He was kind of the anti-Ben Franklin. He was kind of considered a traitor to the U.S. But he worked in an armory for England, and they were making cannons. And the way you make a cannon is not to you don't make a mold of a cannon and then pour iron in it and get a cannon shape with a hole already in it. You make a mold of the whole cannon, then you drill the hole out so the hole is perfectly circular. So you make this big sort of cannon blank, and then you drill the hole. And Rumford noticed in the armory, wow, that makes a lot of heat when you drill a hole in an iron cannon. In fact, you have to keep pouring water over it to keep it cool, or the whole thing just melts back down to molten iron again. And Rumford started thinking about, well, where does that heat come from? And how come when you drill a hole in a cannon, it just keeps getting hotter and hotter, and it doesn't seem to run out? Like if caloric was a kind of stuff, you would think it would run out eventually. Like you can rub your hands together like this and they get warm, right? And if you keep doing that, you don't sort of reach a point where, oh, I'm out of caloric. Now they just stay cold when I rub them together, right? You can just keep making heat as much as you want. And Rumford began to realize that heat can't be a kind of stuff, or it would just run out, and then everything would be cold, and all the caloric would have just leaked out into the air. What Rumford realized that what was causing the heat was the friction of that drill boring into the iron, and that it was the motion that caused heat. And then, in fact, heat is nothing more than motion on the molecular scale, and this is called the kinetic theory of heat. Okay, this recognition that all heat is molecules bouncing around. Okay, if they're moving fast, that means the thing is hot. If they're moving slowly, the thing means it's not so hot. So heat is the transfer of motion from one object to another. And if we ask people, why is my tea hot? What we say is what happened is that the heat from the fire bounced the molecules around faster and faster and faster. So there's no extra thing in the tea. It's water and tea leaves. The water molecules are just moving around faster now than they were before. That's what heat is. So the kinetic theory of heat, the idea that heat is just the motion of atoms and molecules, comes out of the study of how heat is transferred from one thing to another, which during the Industrial Revolution was money. I mean, what you're talking about is making your factory more efficient, making your steamboat, you need less wood to get across the river. You're interested in how to make your machine make the best use of heat, so you need to understand what heat is. So this is a driving force in what's driving people to understand physics better in the 1800s. Laplace and his comets aside, this is the more practical end of physics happening with engineers and factories and things. Well, suppose we want to understand heat as motion. Suppose I've got a balloon full of air and I want to know what happens when you heat it up. Okay, I've always got a balloon in my bag. Let me blow it up a little bit. I won't go crazy with it. We'll just leave it like that. Okay, suppose I want to know, all right, if I hold this over a fire and I heat it up by 10 degrees, what will happen to it? What will happen to it, by the way? What will happen to the balloon if I heat it up? It'll expand a little bit, right? It'll get a little bit bigger. Suppose I wanted to know how much bigger. Well, I'm a physicist. I know how to do this, right? If I want to know what's going to happen in the universe, I need to know where all the things are, and I need to apply the laws of physics to it. So in order to tell what this balloon will be doing if I heat it up, I just need to think of all the atoms and molecules like little planets. And I need to know where they are, so I need to know their locations, X, Y, and Z, where they are in space. And I need to know how they're moving, what direction they're all moving. And then I can calculate where they'll be from a second, in a second. And if they're exerting forces on each other, I need to know the forces they exert on each other. So if there's like electrical forces between atoms, I need to know about that. That's just chemistry. We can figure that out. So I figure out the forces they exert on each other. I figure out how often they collide, and I figure out what the atoms will be doing next, and then next, and then next. Okay? And then I could presumably predict what the balloon will be doing in a few seconds, just like it can predict what Jupiter will be doing in a few weeks. Okay? What's the problem with that idea? Go ahead. There's too many things, okay? But the principle is the same. In fact, Laplace, good old Laplace, said the regularity that we see in astronomy with the movement of the comets exists in all phenomena. Remember, that's where we left out before. The regularity that astronomy shows us in the movements of comets exists in all phenomena. The curve described by a simple molecule of air or vapor is regulated in a manner just as certain as the planetary orbits. The only difference between them is that which comes from our ignorance. In other words, the fact that we can't see the atoms and molecules because they're too small, so we don't know exactly where they are. Probability is relative in part to this ignorance and in part to our knowledge. So Laplace is writing, and remember the title of his essay is an essay on probability. So Laplace is saying, look, this is a situation where we believe that the atoms and molecules in this balloon are following Newton's laws. They're following the laws of physics. They're not unpredictable in any way. We just can't see them, so we don't know what they're doing. So he's suggesting probability as an alternative to knowing exactly what things are doing. Okay? To give you a sense of the impossibility of the task of predicting exactly what's going on in this balloon. 2 liters of gas. It's a little bit less than 2 liters. Let me get up to about 2 liters. Okay, 2 liters of gas, okay, contains 5 times 10 to the 22 molecules of nitrogen and oxygen, okay? That's 5 and then 22 zeros, or if you want it in words, 50 billion trillion. So there are 50 billion trillion atoms and molecules, or molecules, 50 billion trillion molecules, and each of those is an N2 or an O2, right? So it's twice as many atoms, okay? 50 billion trillion molecules inside this balloon. If I wanted to write down all their locations so I could start doing physics on them, right? Because that's what you have to do first in physics. You have to know where everything is. If I wanted to just write down the location of 50 billion trillion molecules, how much information would that be? Well, think about it in computer terms, right? Trillion is like a terabyte, right? A terabyte, you can go to Best Buy and buy a Western Digital terabyte hard drive for $100. Okay, that's 1 trillion bytes, 1 trillion pieces of information. Okay, this is 50 billion trillion pieces of information, meaning that would be like having 10 Western Digital terabyte hard drives for every person on the planet. Okay, there's about 5, 6, 7 billion people on the planet. Okay, so if you gave everybody on the planet a stack of 10 terabyte hard drives, okay, that would be the amount of data storage you would need to record just the location, not even their, we haven't done their speeds yet, just where they are in space of all the atoms and molecules in this balloon. Okay, that is a huge amount of information, right? Probably almost as much information as exists on all the computers on the planet right now, more or less. Okay? Obviously, we can't really do that. Obviously, I can't do with this balloon what your computers do so nicely in Starry Night, which is predict where Jupiter will be next. I can't do that with 10 to the 22 molecules. There's no hope. We need a computer the size of the planet. Okay? Which means if I want to predict what this balloon will do if I heat it up, or even worse, if I want to predict what will happen if I let it go and I want to predict where it will land, okay? The amount of processing that would take would be a computer the size of a galaxy. So we still believe that it's following natural laws. We just understand that in something as complicated as that, we have no hope of doing with the balloon what we do with the planets. So the question is, what do we do? Well, what we do is very similar to what we do when we want to predict or know something about a system that we consider random. Okay? When we want a random event, okay, we do things like we flip a coin, right? Or we roll some dice, or we draw a card from a deck of cards. Okay? We think of those events as being random, but what they're really not random, what they really are is just hard to predict. Okay? If I had a coin and I were to flip it, I don't think I have a coin in my bag because I don't use money anymore. If we were to flip a coin or roll a die, there's nothing magical happening when you flip a coin that somehow uses laws of physics that are different from Newton's laws. The only thing about flipping a coin that's different from the motion of a planet is that we can't flip it exactly the same way every time. We don't know exactly how hard we hit it or what the temperature of the air is in the room or exactly where our hand's going to be when we catch it. So it might as well be random because we don't have enough information to predict exactly where it will land. Same as rolling a die. Okay, a die has 6 sides on it. I roll it. I say whether it comes up a 1 or a 3 or a 4 or a 6 is random. It's not random. If I was Laplace's demon and knew exactly what speed I threw it and exactly how much spin it had on it and exactly the density of the air and exactly how hard the table was it would hit, I could predict the second I let it go, 3, and then it would come up a 3, right? If I was Laplace's demon. But I'm not Laplace's demon. I don't have all that information. So I can pretend, according to Laplace, and according to this new way of thinking about the universe, I can pretend it's random, okay? Which means when I roll a die, it's just as likely to come up a 1 or a 6 or a 5 or a 2 or a 4 or a 3. What does that mean? Does that mean I can't say anything about dice? You just roll them, and whatever comes up, okay? So I can't make any predictions about it anymore. Not exactly. What it means is you can't make a prediction about a single roll of a die, but you can make a lot of predictions about what happens if you roll dice a bunch of times. For example, if you take one die and roll it 600 times, about how many times will it come up 3? Okay? Right. If I got a die, I roll it 600 times, it'll come up about 100 3s, about 100 6s, about 100 1s. It won't be exact, but it'll be about that. And the more you roll it, the closer you'll get to being able to make a good prediction. Suppose I roll 2 dice, okay? And this is something that happens in a lot of board games. Monopoly, right? You roll 2 dice, okay? So when you play Monopoly and roll the 2 dice, it doesn't matter if you roll a 1 and a 5 or a 2 and a 4. You move your little shoe 6 spaces, right? When I roll 2 dice, is there any number that comes up more often than some other number? If I add them up, what is it? Okay. Anybody know? You roll 2 dice. Is it the same chance I'll get a 12 as a 6? Why? Right, there's only one way to roll a 12, right? You've got to get a 6 and a 6. But there's a bunch of ways to get a 6. I can get 2 3s, or a 2 and a 4, and a 5 and a 1. That means when I roll 2 dice, some things happen more often than others. The one that happens the most is 7. Okay? If you roll 2 dice and do it a bunch of times and write down the total, okay, what you'll find over time is that you roll more 7s than anything else. Why? Because you can get a 7 with a 6 and a 1, or a 2 and a 5, or a 3 and a 4, or a 4 and a 3, or a 5 and a 2, and a 1 and a 6. Right? So if I make a graph, actually, of the probability, it looks something like this. Okay? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, that's based on probability because there are 6 different ways to get a 7, but only one way to get a 2. The trick is, that's not a theoretical graph. The way I made that graph is I took one of my college classes, I gave them all 2 dice, and made them spend 20 minutes rolling 2 dice and then writing down what numbers they rolled. And then I took all of those numbers together. So this is actual data, not just theory, about what happens if you take 2 dice and roll them. Let me see the numbers. That's about 100, so that's about 1,000 dice rolls. So this is the equivalent, I mean, I spread it out amongst a dozen or so kids, but this is the equivalent of taking 2 dice and rolling it 1,000 times. What do you get? You get a pattern that is absolutely predictable. Okay? It's always happened the same time. I've never one day done this in the class and had more 12s than 8s. Okay? Is it possible to have more 12s than 8s? Is it possible that I could hand you 2 dice and you could roll it 100 times and roll snake eyes 1-1 every time? Yeah, it's totally possible. Will it happen? No, it's not going to happen. Okay? And probability is a weird kind of way of thinking about the universe because we have to both accept that something is possible and also accept the conclusion that it is absolutely not going to happen. The probability of you taking 2 dice and rolling two ones, rolling a 2 with the 2 dice, even 5 times in a row, is such that you would have to do it the age of the universe to ever expect that to happen with a 50-50 certainty. Okay? I would bet any amount of money. I would let you hold a gun to my head and say, you roll those 2 dice and you roll snake eyes 100 times in a row and you can pull the trigger. All right? It is absolutely certain in a weird sort of way that that won't happen. And why is it a weird sort of way? Because it's not really certain. It's highly, highly, highly improbable. Okay? What Laplace is laying out in 1812 is the mathematics for dealing with probability in a coherent way. And what scientists are realizing in the middle of the 1800s is sometimes that's all we've got. If I want to fill a balloon full of air and ask what's going to happen to the balloon, I can't predict exactly what's going to happen inside that balloon. But I can say, on average, most of the molecules in this balloon will be moving at such and such a speed. If we think about this room's a big container full of gas. Okay, it's about 70 degrees in here. If we could see all the nitrogen and oxygen molecules, they're all moving around, bouncing off of each other. They're not all going the same speed. Some of them are going faster, some of them are going slower. But they're not moving at random, they're bouncing off of each other following the laws of physics. But we can't know what they're doing, so what we can say instead is, on average, a molecule in this room is moving with such and such a speed, and such an energy, and such a rotation. Okay? And if we imagine rolling dice 50 billion trillion times, we can be pretty confident that those probabilities will turn out the way we said that they would. Okay? This way of thinking about heat and temperature and gases was fully developed in the late 1800s, 1859 to about 1870, by James Clerk Maxwell and Ludwig Boltzmann, both with outstanding 1900s physicist beards. The name statistical mechanics is set up to be a direct contrast to the way mechanics was done before. It's not Newtonian mechanics. It's not, I predict exactly where everything is. It's, I know some general rules, and I know there's a lot of stuff in there, but I'm going to predict probabilities that certain things will happen. For example, for the gas in a balloon, you can use mathematics to estimate how fast things in that balloon are moving. This is a graph of energy of a particular molecule. So this way, these are fast-moving molecules and these are slow-moving molecules. And the vertical axis is just what fraction of the molecules are moving at that speed. And what Maxwell and Boltzmann derived is that there's a very predictable distribution that doesn't look too different from the graph I got with the 2 dice, right? It's very improbable to roll a 2, pretty probable to roll a 7, very improbable to roll an 11 or 12. In this room, it's very unlikely that there's a molecule zipping through this room really fast. Very probable that they have about this energy. They could have a really small energy, but it's very unlikely that they have a molecule in this room just stop because some other molecule is going to hit it and it's going to start moving again. So I can't predict exactly what the atoms and molecules in this room are doing, but I can say about 1 billion trillion of them are moving these fast, and about 2 billion trillion of them are moving that fast, and about 1 of them is tearing through here really fast at any given instant, because it just happened that this molecule was sitting here, and 2 other molecules hit it at the same time, and it goes off twice as fast as all the other molecules. That happens every once in a while. Okay? This way of thinking about the universe, though, is a big departure from what Laplace was saying about his imaginary intellect, that what we should be doing is predicting exactly what's going to happen in the future. It's a letting go of that whole idea that we can predict exactly what's going to happen in the future. And what we replace it with is the idea that we can know probabilities about the future if we know something about the whole system, not its tiny, tiny, tiny little parts. So this idea that there's unpredictability in the universe is a fairly new one. And it's a different kind of unpredictability than we might have thought of with Newton. For example, with Newton, we might have looked at something like a pool table and said, balls on a billiard table are just following Newton's laws. They're just exerting forces on each other and bouncing off the rails. I should be able to predict exactly what will happen. But if I do something really complicated, like at the beginning when I hit the cue ball into the triangle of 15 balls that are all racked up, Every break is different. Even if I try to do it exactly the same way, it always turns out different. And the reason is there's a lot of balls, and tiny, tiny differences in where I hit that ball will make a big difference in the end. That is an even bigger situation if I'm talking about something like the air. Okay, if I'm talking about the air in this room, there are still deterministic laws that tell me where every atom and every molecule is going to be every second. But the rules that they follow are much more complicated than Newton's laws, and they're what's sometimes called nonlinear effects. So I'm going to really quickly, I've got about 20 minutes to do this, so I think I can get to the end, talk about what we mean by linear behavior versus nonlinear behavior. Newton's laws of motion are linear. What do we mean by that? Well, if you think about what it means in algebra, a linear equation like y equals mx plus b just means that nothing's squared in it, and that's one thing we mean by linear. One result of an equation being linear is that if we make a small change on one side of the equation, it results in a small change on the other side of the equation. So f equals ma, we just rearrange that algebraically to be f over m equals a. So if I've got a ball with a certain mass, I exert a certain force on it, how much does it accelerate? That's what I can calculate with this equation. The heaviest ball I have is a cross ball. Weighs 2 kilograms. I exert a force on it of 20 newtons. The acceleration should be 20 newtons divided by 2 kilograms, or 10 meters per second per second. Suppose I change that force from 20 newtons to 21 newtons. Okay? Then the acceleration will be 21 newtons divided by 2, which will be, 10.5 meters per second. Suppose I changed it to 22 newtons. Then the acceleration will be 22 newtons divided by 2 kilograms, or 11. So if I change one of these numbers on this side of the equation a little bit, this number changes a little bit. Okay? That's what we mean by a linear equation. If I change the mass from 2 to 1.9, I don't expect you to be able to do that one in your head, but it's 11.58 meters per second. So Newton's second law is an example of a linear equation. And all that means is that a small change on one side leads to a small change on the other side. We owe our ability to make these easy predictions that Laplace was talking about to the fact that a lot of the equations that describe our universe are linear. Okay? For example, if I throw a ball a little bit harder by exerting a little bit more force on it, it goes a little bit further than it would have gone. That is true because the equation f equals ma is linear. And what that means is that if we can fairly closely reproduce the starting conditions in a physical system of balls or whatever, the end condition is fairly easily reproduced. This is a picture of a cluster of arrows in a target. And if any of you took the archery class with Russell, one of the first things you focus on is not hitting the center of the bullseye every single time. It's getting your arrows nice and clumped together in a little group like that, because that means that every time you're doing the same thing, you're pulling it back the same amount, you're holding your arm steady, your release is the same. Okay? You're starting with the same starting conditions, so you end with pretty close to the same ending conditions. That is possible because the laws of physics that describe the flight of that arrow are linear. That if you change something by just a little bit here, it changes something by just a little bit there. This is really obvious if you look at people whose job it is to throw balls around and kick balls around and make the same thing happen every time. If you look at professional athletes, I just went to the ESPN stats site and pulled up. The top graph is field goals by NFL American football kickers. The second one is free throw percentages from NBA basketball. And the bottom one is first serve percentages from professional tennis players. And if you look at the statistics in the top graph, the highlighted column percentage, NFL field goal kickers can kick about 91%, 92%, 93% of the time, kick that ball and make it go through those two vertical posts. Okay? It's even more impressive if you look at extra point percentages, right? Because the difference between a field goal and an extra point is extra point, you're always exactly the same distance away from the thing. Okay? It's always exactly the same way you practice it. So almost all NFL kickers have 100% extra point percentage, which means they know that if they kick the ball this hard from this spot, exactly where it's going. every single time. Okay? Free throw in basketball is the same thing. Okay? It's a little bit smaller target, so it's not 100%, but still, if you are standing at the same spot and the basket's always there and it's always the same height, and you learn how to throw it the same way all the time, 80, 90% of the time it goes through the hoop. Okay? Contrast the predictability of what happens, and you don't have to be a professional athlete, right, to be able to do this. We all, even if we're, only slightly coordinated, Selena, can throw a ball and make it go basically where we want it to go, right? Okay? And even if we've never thrown this ball from, look, I'm not on the ground, right? I'm 3 feet up off the ground. I can know from how my muscles work exactly how to make the ball go kind of where I want it to go. So that predictability is due to the fact that we live in a universe where most of these equations are linear ones. Look at something like this, though. It's not hurricane season right now, but this is actually a track from Storm Isaac from a couple years ago. Think about this in terms of Laplace, right? He says we know where something is now, and then now, and then now, and then now. We should be able to predict it. But look at this prediction, okay? Here's the hurricane, and these are in days. So 1 day, 2 day, 3 days. But instead of predicting exactly where it's going to be, you get this cone of maybe the hurricane will be somewhere between here and here. And that's a pretty wide cone, right? It goes from, where are we on? It goes from the Alabama-Mississippi border all the way to Texas. So that's, 600 miles? After 3 days, we're not sure where it's going to be to within 600 miles. The weathercasters sometimes call that the cone of uncertainty. If we just take that cone of uncertainty and the width of it and move it to a baseball diamond with the same width, if a baseball pitch was as unpredictable as a hurricane, it would be going behind the batter as often as it goes over the plate, right? If we take that cone of uncertainty and imagine that baseball pitches were that uncertain. It's very rare that a baseball pitcher throws that far off. So there's something different about hurricanes and baseballs, is the point of this. And there's something different about the laws of physics that govern hurricanes and the laws of physics that govern baseballs. What is the difference? The difference is that the laws of physics that govern hurricanes are nonlinear. Okay? It is not true that a small change at the beginning leads to a small change at the end. Okay? If we look at a situation like a rising column of smoke, which you can think of as a hurricane in miniature, in some situations the behavior is sort of very common linear, but as the temperature increases, or as the density of the air decreases, or as there's movement in the air in the room, that behavior quickly becomes what we sometimes call turbulent or chaotic. Okay? In this situation, if you have two air molecules that started close together at the beginning, they're going to wind up close together at the end because they rise up pretty much vertically, and you can predict where they're going to be. But in this situation, the more turbulent situation, two molecules that started close together at the beginning, at the end might have traveled very, very different paths and might wind up very, very far apart by the time they get to the top of the image. So two air molecules that started in similar states at one point might wind up in very different points at the end. And a tiny, tiny effect on that motion, say a butterfly on the other side of the room flapping its wings, could completely change the motion of that rising column of air because it is so sensitive to the motion of all the air molecules around it. And because the equations that govern the motion of air are not as simple as F equals ma. I'm going to put them up there just to scare you a little bit and just so you see, just with your eyes, that obviously that's a more complicated equation than F equals ma, right? It says the density times dV dt plus V dot del V equals negative gradient of the pressure plus the divergence of the stress plus the force. What does that mean? In words, it means that if you want to know pick a little bit of the air and how fast it's moving, and you want to know how that changes over time, what affects it? What affects it is the density of the air, the difference in pressure between one point and another, in other words, it's high pressure, low pressure, the stresses and forces that are acting on the air, in other words, if there's gravity pulling the air down or friction pushing the air up from other air moving past it, the velocity, and the change in velocity from one point to another. So if you've got an air molecule here moving such and such a speed, and ones here are moving faster, and ones here are moving slower, that friction is going to cause that one in the middle to move at a different speed. If we simplify this and take out all the stuff that's not about the velocity and just call it stuff, the equation says the change in velocity equals a bunch of stuff plus the velocity times some other properties of the velocity. So the velocity appears in the equation twice. If we think about what linear means in algebra, an equation like y equals x squared is a nonlinear equation. It's because it's not just x, but x times x. Right? This equation is the change in velocity is a bunch of stuff plus the velocity times the velocity, which means if we change the velocity a little bit, that magnifies the effect on the other side of the equation. So these equations are much more sensitive to changes in one side. And a change in one side of the equation can cause a big change on the other side of the equation, not a small change. Which means that whereas when I throw a ball, if I throw it a little bit harder, it goes a little bit further. If I blow a little bit harder on one of these air molecules at the beginning, it could wind up going a lot further at the end. That's what we mean by nonlinear behavior. Okay? The only reason to do this is to give you a sense of, if you hear the word nonlinear when reading over some of William Thompson's stuff or Ralph Abraham's stuff, you'll know that there's a mathematical meaning behind that. What does it mean? It means that because the term appears in the equation twice, if you change it a little bit, it has a big effect on the other side, not a small effect. What is an example of this? Something like feedback, right? Any of you that play an instrument that's electrical, that you run through an amplifier, are familiar with the phenomenon of what happens when the sound coming through the amplifier is picked up by the microphone and then goes through the amplifier again and made louder, and then it's picked up by the microphone louder and goes through, you get this wah sound that busts your eardrums, right? Why does that happen? It happens because the volume of the sound coming out of the amp, because it's being fed back through the microphone, depends on the volume of the sound coming out of the amp, right? So if it changes by a little bit, that feedback goes through the system and snowballs into this loud, horrible sound. Okay? Feedback is one example or one cause of nonlinear behavior, behavior where tiny changes have big results. This is important when you start talking about something like a complicated system like the atmosphere. If I want to predict what's going on with a hurricane, okay, it's not possible to know where every single air molecule on that hurricane is. We can't even do it with a balloon. What I have to do is think about the pressure and temperature in different places on the Earth and try to make a prediction. But those predictions are very nonlinear, which means that little changes can snowball into big effects, which is why when you watch the weather, there's only a 5 or a 7-day forecast, not a 30-day forecast, right? No one knows what the weather is going to be 30 days from now, because any slight change in the weather today would snowball into a completely different day 30 days from now. This effect was summarized by a scientist named Lorentz in the 1960s, was the talk that he gave about this, as the butterfly effect. Meaning that if I'm trying to predict the weather here in the United States, that a butterfly flapping its wings in Brazil 2 weeks ago could change whether or not today is a sunny day or there's a tornado today. That these tiny effects, the motion of a couple of air molecules could move a few other air molecules and cause a slight gust of wind that moves this bigger system, that causes a low pressure system that winds up creating a tornado instead of a nice clear sunny day. That in order to predict the weather exactly, you would have to know every tiny effect on the atmosphere, including the motions of butterfly wings thousands of miles away. Obviously, we can't do that, okay? Which means that we have to think about something like the weather completely differently than we think about planets going around the sun. That we can't think of it as a system that we can predict exactly what's going to happen. We have to be more clever. It's still a dynamical system. We're still looking at how it changes over time. We're still trying to predict something about it. But it's not the same kind of predicting that Newton let us do. It's a different kind of predicting. Okay? I tend to talk about these things from a physicist standpoint because I'm a physicist and that's the language that I speak. But you could say the same thing about science in this time. Remember, we're talking about 1830s, 1840s, 1850s. If we talk about biology, what's going on in biology in the 1850s is Darwin. Okay? The Origin of Species was 1859, I think. Okay? What kind of theory is natural selection? Is it a theory that says you have these kind of animals and then they have these kind of babies and exactly this is how things will evolve and I can predict what things will happen in the future? It's not that kind of theory at all. It's a theory that's highly contingent. In other words, it matters a lot on chance and randomness, but it's a predictable pattern over time. If we look at not just individual organisms, some of them live, some of them die, who knows? Right? Just by accident, a perfectly healthy and well-adapted organism might find itself someplace with no food and starve to death. Or it might just, I don't know, trip over a rock and fall off a cliff. Who knows? Okay, stuff happens like that in nature. But if you look at 100 organisms, or 1,000 organisms, or 1,000,000 organisms, over time, there's a pattern, just like over time there's a pattern when you roll a dice 1,000 or 1,000,000 times, which is the ones that are slightly better adapted to their environment have slightly more offspring that causes certain traits to change over time and to dominate a population. So natural selection isn't a predictive paradigm the way Newtonian physics is. It's much more like statistical mechanics. It's saying we can't say what will happen with individual organisms in an ecosystem, but we can say what will happen on average with thousands, hundreds of thousands, millions of them reproducing over hundreds, thousands, millions of years, that certain patterns will emerge in terms of adaptation, in terms of change gradually over time. So this letting go of a kind of minute-by-minute prediction of every single thing that's happening in the universe and replacing it with thinking about the system as a whole and drawing conclusions of the system as a whole and predicting not exactly what's going to happen, but trying to model what's probably going to happen, is this shift from the Galilean dynamical mentality to what William Irwin Thompson calls in his curriculum in consciousness, the complex dynamical mentality. So to sort of wrap up almost exactly on time, this approach to making predictions about the universe, it starts with Galileo and Newton. Galileo and Newton were still a little stuck in the geometric mentality, but by the mid-1800s, this Galilean dynamical mentality was how you did science. Record current conditions, derive laws about them, make predictions, and you'll know everything. According to Laplace, if you're smart enough, you can predict the whole future of the universe this way. That's, at least in physics and in science in general, what we can consider the climax of the Galilean dynamical mentality. Laplace's statement that if you know the laws of physics of the universe, the future is as clear to you as the past. There's nothing left uncertain. Okay? What we realize almost immediately after Laplace says that is that from a practical standpoint, it's literally impossible to do that in many cases. You can't, it's not just that you can't see atoms and molecules. Even if you could see them, there's not enough paper in the universe to write down where they are to start calculating what they're going to be doing next. So instead of predicting what systems are doing exactly, we invent new approaches, okay, to looking at physics, biology, such as we consider probabilities, we consider general trends and overall behaviors of a system as a whole, and we create models that approximate a system. If you ask how the meteorologists on the news figure out what the weather's going to be, I don't know, what's today, Wednesday, what the weather's going to be on Saturday, or whether it's going to snow or rain or sleet tomorrow night at 3 a.m., how do they do that? They have computer models on their computers, bigger computers than we have, more powerful, faster computers, that have models for how the atmosphere works. They don't record every location of every atom and molecule in New York State and try to figure out what they're going to be doing next. They have the pressure here is so-and-so, and this is what happens when two air masses meet with different pressures and temperatures, and they're approximations of nature. They're pretty good. They're better than they were 25 years ago because our computers are better, but they're still not perfect. Sometimes they say it's going to rain and it doesn't rain. Sometimes they say it's going to snow 6 inches and it snows 18 inches. Okay? So we have developed an approach to figure out what's going to happen in a complex system Not by trying to figure out exactly what every piece of the system is going to do, but by creating a little toy model version of it that lives in our computer that kind of usually does mostly what the real thing does. This approach is the beginning of what Thompson calls the complex dynamical mentality, looking at the universe not as individual little interacting things we have to know exactly what all of them are doing, but looking at it in terms of interactions on a bigger scale between more complicated things. This is just like Galileo was the beginning of the dynamical mentality. This idea from the middle of the 1800s is the beginning of the complex dynamical mentality, and it's something that we're still figuring out. Okay? I'm not sure this one has peaked yet, because you still have people who refuse to believe that global warming is a real thing. You still have people that doubt that computer models are the right way to figure out what's happening to our atmosphere. So I think that this is a transition, and this will come up in all your classes here as you get closer to the end of the year. These last stages of the spiral are stages that we're either at the climax or near the climax or maybe not even quite near the climax of yet. So the complex dynamical mentality is something that it goes through quantum mechanics in the 30s, and if I come back to talk to you one more time this year, that's probably what I'll talk about, is the fact that Laplace tells us it's just too much information to know where every atom and molecule in a balloon is. What happens in quantum mechanics in the 30s and 40s and 50s is people come along and say, you know what, it doesn't even make sense to talk about where an atom is, because that's not information you could even imagine having. Even if you were Laplace's infinitely smart demon, there's no way to even assign a position to an atom that's 100% certain. So that's the next phase in kind of accepting this mentality, is believing that, that in some sense this information doesn't even exist. It's not even there to be had. Not only can we not have it. What conclusions we can draw from this complex dynamical mentality? In other words, okay, now we have to do science a different way. Is all hope lost, or can we learn different things about the universe than we could before? So that'll be the topic of another visit. Okay, thanks.